Hello everyone. This is a question from the book Pathfinder on the topic electrodynamics. So let's read through the problem once. A parallel plate capacitor is filled with two layers of different materials A and B. The material A has a dielectric constant K1 and conductivity sigma 1. Ideally, the conductivity of a dielectric constant should be 0, but here in this case, it is not 0. So some charge will leak through the capacitor plates from the top to the bottom. Also, the material B has a dielectric constant K2 and conductivity sigma 2. The capacitor is connected across an ideal battery of terminal voltage V. Ideal battery means there is no internal resistance. So we have to find the electric field in the material A. Also, we have to find the total surface charge density on the interface of the two materials. So let's start this problem. The above combination I have already copy pasted the photo here, and this can be redrawn to look like this. So the capacitors and the resistances, their combinations can be connected across the battery in parallel. So the effective capacitance we can write down, but before that we need to write C1 and C2. So C1 can be written as epsilon naught K1 A upon D1. Similarly, C2 we can write as epsilon naught K2 area upon D2. Let us write down the value of the resistances also. So R1 can be written as D1 upon sigma 1 into area. Similarly, R2 can be written as D2 upon sigma 2 into area. So equivalent capacitance C effective in a series combination can be written as C1 C2 upon C1 plus C2. And if we put in the values of C1 C2 from above in this equation, and after solving we will get epsilon naught K1 K2 into area upon K1 D2 plus K2 D1. Now on similar lines we can write R effective. R effective can be written as R1 plus R2. And by putting these values here we can get R effective also, and once we get R effective we can calculate the current in the steady state. Current can be written as potential difference across the terminals of the resistances divided by effective resistance R1 plus R2. So if we plug in the values we can get the value of current. So current comes out to be B into A divided by D1 upon sigma 1 plus D2 upon sigma 2. So we are going to use these values in the electric field calculation. So for electric field calculation, first of all we need to calculate the potential differences across C1 and R1 or C2 and R2. Potential differences across C1 and R1 will be same. Similarly, the potential difference across C2 and R2 will be same. So let us call V1 as the potential difference across the first capacitor or the first resistor. So V1 can be written as I into R1, and if you put the value of I and R1 here and simplify, then V1 can be found out to be V into D1 sigma 2 divided by D1 sigma 2 plus D2 sigma 1. Once we get this value of V1, we can calculate the electric field in the first capacitor. So electric field in the first capacitor can be written as V1 by D1, and on simplification D1 will get cancelled, this D1 will get cancelled, and we will be left with V into sigma 2 upon D1 sigma 2 plus D2 sigma 1. On similar lines we can calculate E2 as V into sigma 1 upon D1 sigma 2 plus D2 sigma 1. So this becomes the answer to the first part of the problem. For the second part, we need to calculate the surface charge density near the boundary. So We will draw the circuit once more and apply Gauss law near the boundary of the two dielectrics. So if we construct a Gaussian cylinder and E1 and E2 are the respective electric fields across the two dielectrics, then the net flux of the electric field, we will take the flux of the electric field coming out as positive and the flux of the electric field coming inside the cylinder as negative. So the net electric flux can be written as E2 minus E1 into area, and this can be equated to charge near the boundary upon epsilon naught. So if you divide QB by area on the right hand side, we will get our desired value. So E2, and let us cross multiply by epsilon naught also. So epsilon naught into E2 minus E1 gives us sigma near the boundary. And if we put the values of E1 and E2 that we have got earlier, then we will get sigma boundary as epsilon naught B into sigma 1 minus sigma 2 divided by D1 sigma 2 plus D2 sigma 1. So coming back to the problem, the correct options will be for 22nd, the correct option will be D, and for the 23rd part, the correct option will be B. I hope the solution is clear to you.